Welcome to another edition of BS&BEER Canada. My name is Aaron Jones. I am a carpenter and a builder. Whoops, over, wrong way, over here. I'll never get this right. Grand Island, New Brunswick, Canada. Closet blower or not. For quite a while now, we have maintained a minimum standard of net zero ready in all of our new construction, and we try and do the right thing for the building every time. Tonight, I am drinking a leftover Harrison Irish Red from the Dartmouth BS&BEER Canada Building Science Symposium. And I'm going to hand it off to you, Connor.
Hey everybody, my name is Connor Malloy. I'm a designer, builder, and educator based in Toronto. I run a consultancy called Supernormal Buildability. We help builders learn how to sequence and build airtight, high-performance buildings. And I teach at George Brown Polytechnic in Toronto, where we teach young carpentry students how to build better, how to understand control layers while we're teaching how to do framing and layout and forming. And it's an important thing to do. I am giving up some things for the month. I'm on Stay Classy tonight. This is a non-alcoholic IPA from Bellwoods, my favorite brewery in Toronto. And I'll toss it over to you, Jeremiah.
Good evening, everyone. I am Jeremiah Summer. I'm a builder in Southwest Ontario. Our small crew is really into kind of pushing the envelope on building envelopes and learning using building science and a lot of the great teaching that is available in this day and age, and from people like Gord and the people at Building Knowledge Canada too. So we really have found that education is such a key part for our team and for us to be able to develop high quality builds. And so formats like this are just one way for me to kind of stay involved in the sort of building science side of things and always find something interesting to learn from people.
And I'll just jump in here. Unfortunately, I don't have the logo today because I'm Sean Sanamore, manager of Revive at Etro Construction. We're focusing on restoring, reinventing, and rehabilitating buildings. And I'm at the Carbon Leadership Forum BC Symposium, and we're got a bit of a dinner break before the awards start, and we're celebrating how we're reducing our embodied carbon in our buildings and showcasing some exciting buildings across Canada. So I'm actually still drinking my coffee out of my Veta Windows mug, and I will definitely be having a few beverages shortly. So enjoy your beverage, whatever you have. Enjoy the show, and Aaron, I get to turn it over to introduce a legend in Canada, a legend in North America, Mr. Gord Cook.
That's awesome. But actually, I'm going to hand this off to Jeremiah since Gord is actually Jeremiah's guest. So, Jeremiah, if you would do the honors of introducing Gord to us, please.
Absolutely, I will. So, as many of you on this call probably already know, Gord is a highly respected professional engineer, educator, and consultant, and has over 35 years of experience in the residential construction industry. Gord is the president of Building Knowledge Canada and a partner at Construction Instruction. And I'm just going to plug Construction Instruction for a minute. I reached out to Gord, probably 2 years ago with a question, and he promptly got back to me, which was wonderful. And he recommended that I attend the HVAC for builders. I can't quite remember the name of the course at Construction Instruction in Denver, which I did. And I highly recommend it. It is really great experience for builders, anyone learning to or wanting to learn sort of high performance building, but even and get a better handle even on mechanicals. And they have a great lab and a really awesome setup. So I'll continue on. Gord specializes in applied building science, energy efficient housing, HVAC innovation, and indoor air quality. He's also dedicated to improving health, safety, comfort, and durability and energy efficiency in both new and existing homes. Gores also trains builders, renovators, HVAC contractors, and energy advisors on high performance building techniques that contribute to a more sustainable living environment. And tonight, Gord is going to talk to us about right sizing mechanical systems for high performance homes. I'll turn it over to you, Gord. Thank you.
Well, thank you so much, Jeremiah. Thanks for that plug to CI. I'll just, while I'm bringing up the presentation, I'll just tell folks that it is indeed a cool facility, 12,000 square foot facility in Denver. And the key to it is it's all hands-on. So we demonstrate how HVAC works, help you make better choices. We have other classes on high performance enclosures and advanced building science. Go on the website, constructioninstruction.com. There's also a free app that apparently is still the largest app in the construction industry, designated, or I would say focused on building science, all kinds of cool animations on there. And as Jeremiah said, we thought we'd talk about tonight in kind of a whirlwind tour of this key topic. We've called it right size mechanicals, but for the most part, it's just a reminder of the mechanical side. Before the rest of you joined the call, we were chatting about, what is the challenge? And builders across North America say to me all the time, as they approach higher performance, they seem to be dragging their HVAC contractors along. And perhaps it would be valuable for you to know that my start in this industry was designing and building back in 1984, something called a heat recovery ventilator. And you can imagine in 1984 trying to get mechanical contractors and builders to use that and what lengths we had to go to. And to this day, that V in HVAC is still a struggle for many contractors, many builders, many contractors to get their heads around. So tonight, in a, let's say, whirlwind, just under an hour, we'll talk to you about mechanical opportunities and risks. Some of the things that I want to talk about is just to remind all of us, and that we need to remind both our contractors and our homeowners, that things have changed in the way we use houses, the way we build houses, the materials that we use, and the expectations we have in houses. And that has huge impact on HVAC design and performance. I will give you the essence of HVAC design. I really want to show you just how straightforward it is. It's just a math exercise. So we'll chat about that. And then a few options, a few thoughts about some changes that are taking place in distribution and performance verification. I do want to touch on, as I mentioned earlier, ventilation, filtration, and humidity control, because they're not always in the name. They're not always part of HVAC. They should be, ventilation should be, but we need to keep that in mind. And as we get started, I'll just remind you that builders and HVAC contractors are in the business of, at the top left, in the business of replacing heat that's been lost through the building in winter, removing heat from buildings that's been gained through the building. And this really brings up the idea of, say, of passive house. Some of you may be passive house advocates. And the premise of passive house is, what if we didn't need a heating system? What if we didn't lose any heat and therefore we didn't need to replace any heat? Would that be possible? And the answer is, of course, it's possible. May not. We may need still some supplemental, but fundamentally, we are trying to reduce, most of us on this call are trying to reduce the loads and then replacing just as little as we need. What I want to remind you is those loads on the left-hand side are intermittent. They come and go season to season. The loads that are actually continuous are the fresh air and the filtration, fresh air, ventilation, and filtration. Those are needs that pretty much whenever you're breathing, you need fresh air and you need filtered air. And any continuous breathers on this call would then say, gee, I guess therefore I need that fan running all the time. What many of us in Canada have understood, humidification, houses being dry, that's less and less of an issue because we're building tighter houses. But a new piece on the block for many of you in the country is dehumidification. So I just want to highlight those are the objectives that we want to walk through. I do want to start with and remind you that when I say HVAC design is based on some pretty simple math, the math starts with some basic assumptions. That is, what does a heating cooling system do? And we need to be aware that when your HVAC designer, mechanical contractor designs a system, they're designing it to maintain a 24 degrees Celsius setting in the summer, plus or minus 2 degrees, 22 degrees Celsius in winter, plus or minus 2. You see the humidity numbers, which we'll come back at. This is an important note because there are many clients who would say, wait a minute, I don't want it 24 in the summer. I want it 22 or 20. I've had clients who say I wanted 18 in the summer. This is one of the changes that I hinted at earlier. People's expectation of what temperature they want. Some would say the HVAC design is behind the times. Some would say, well, maybe we need to re-educate clients as to what is the right temperature to live at. But it does put stress on us when we think that the system we've designed is good to 24 Celsius plus or minus 2. Many of you would say, my clients want it much tighter than that. They want it plus or minus 0 between top floor and bottom floor. But those are sort of the comfort basics, if you will. In terms of important changes that affect our industry, I alluded to homeowner changes. On this call, people know that you've doubled performance of windows, you've doubled performance of walls, you've cut air leakage by as much as 80% in houses. You have made houses needing far less heat, far less cooling than ever before. It should encourage you to know that the industry, the HVAC industry, has made some changes that will be helpful to you. One, there is a new version of an old standard called F280, which is the standard that's used to design heating and cooling systems. It was recently updated 5 years ago, updated again shortly here, and it is much better at understanding the loads in houses. So some of our old rules, our old thoughts need to go by the wayside because the new standard gives us much better thought. Two, the Residential Air System Design Manual that's presented by HRAI does a better job of understanding how air moves through ductwork, how air moves in houses. So that's useful to us. And giving us some allowances, you'll see there on the page for rationalizing return air grills, recognition of low load houses, those kinds of things, improved guidance on duct leakage and so on. And then many of you will recognize the new variable equipment options, both in furnaces and perhaps most importantly, heat pumps. So as much as I can say the industry hasn't responded, certainly at the top end, the industry has responded. Better design tools, better equipment tools, better recognition of the challenges in houses. So that should be useful to you. And I'll mention again that the things that you do to improve houses, like better air tightness, better wall insulation, better insulation overall, better windows, really does do a nice job of lowering heating cooling loads, winter and summer. And that makes high performance HVAC, such as heat pumps, much more viable. So in many cases, HVAC contractors will say to you, well, it's just not the way I've done it. And I don't know if that's going to work. And you can put them at ease and say, wait a minute, let's just understand. My houses are nowhere near what old houses are, or I'm doing renovations, as Sean said, doing renovations of historic houses. I'm changing the dynamics of how that houses work. So you don't need to hold yourself to your old rules. Let's talk about some new ideas, some new rules. So keep that in mind. And I'm not going to spend time on this slide other than to say this. When you do a heat loss and heat gain on a house, it's basically 3 formulas. How much heat flows by conduction through walls, floors, and ceiling? How much heat moves through the flow of air, either air leakage or ventilation? And how much heat flows through specifically windows, translucent, transparent elements by radiant gain? 3 basic formulas. And yes, there's some bits and pieces of how basement works and so on, but fundamentally, it's pretty simple formulas that define the proper size. 2 things to know about this. It's actually pretty simple. What do you need to know? Areas, temperatures, insulation levels, nothing too fancy. There's no fancy calculus in this at all. But 2, it's not perfect. It's just a prediction. It's the answer is that you get is never right. It's just a good guidance. So it starts with, and so what you hear from folks is, well, I've been doing this a long time. I understand this size house. Okay, but start with the basic math and then decide what you want to do in terms of creativity. The basic math should help you design a house. And here's a little example of just how dramatic the changes have been. If you took a 2,275 square foot house, Southern Ontario, just as an example, but do it across the country. In a house built to the code levels across the country in the year 2000 would have seen a heat loss, a need for 62,000 BTUs. You would have put in an 80,000 BTU furnace in that house for 75. By the time you get to net zero, you're down to 24,000 BTUs, not quite a third of what you were before, but certainly under half. Even if you're just doing an Energy Star house, you've cut the loads in half. Look what's happened to the heat gains, the air conditioning loads, and again, cut in half over a relatively short period of time, 25 years. And We need to help our mechanical contractors understand that, show them the loads, encourage them to do the loads. From their perspective, it's very helpful on the right-hand side. To deliver that amount of energy used to take 1,200 cubic feet per minute of air running around the house. Now you cut that in half. And imagine the opportunities, maybe the risks, but the opportunities of smaller ductwork, fewer diffusers, fewer registers, maybe less return airs. Tremendous opportunities once we get our head around. In many contractors' case, they're going to say, I've been doing this for 30 years. Right, then stop, because what you were doing 30 years ago was twice as big as what it needs to be now. Rethink it, go back to school. This is a significant change that we need to understand. So keeping that in mind. And as a little example of that, the big drivers of this over on the left, when we look at a heat loss, heat gain of a typical house, 30% of that is due to air leakage. And everybody on this call, you said, Aaron, you're a blower door junkie. If you're a blower door user, you're nowhere near 30% leakage, 30% of the heat loss being air leakage. You're down around 10%. You've made a dramatic drop. Over on the right-hand side, and one of the big challenges, and I'm willing to admit, is this incredibly variable load called heat gain through windows. 50% of the size of an air conditioner is due to heat gain through windows. And do we want more windows or less? All of you building incredibly efficient houses, but I'll guess that your clients still want bigger and more of them. And that's a challenge because it's an intermittent load. The big portion of the load of windows you'll see in a second is actually the radiant gain. So if the sun's shining on it, it's a huge load. If the sun isn't shining, it's not a very big load at all. And that puts huge stress. That alone makes us have to change the way we design our systems. The intermittent nature of the load is absolutely critical to understanding comfort and the design of HVAC systems. So very important that we understand that. I wanted to just mention air leakage. I mentioned that there are simple algorithms. Well, envelope air leakage is not a simple algorithm. The good news is we have 30 years, 40 years now of data and research. It's actually called the Alberta Infiltration Model. The Alberta Infiltration Model, you can imagine where it was developed, University of Alberta in Edmonton 40 years ago, and been updated since, that determines how much air leaks in and out of a house, depending on the geography, depending on the type of the building, the height of the building, so on and so on. So that's the most complicated formula there is in predicting house air leakage or predicting heat loss, heat gain. But that said, it's definable, it's predictable, and I would say commit to blower door testing, and more importantly, then commit to handing that information to your HVAC designer and having them going into their software and adjusting the number and actually encouraging them and showing them, hey, put in my number there. It'll make a nice difference to the way this house works. So that's important to understand. The algorithms and how they're used within the building is useful. I wanted to show you a highlight. I kind of mentioned it earlier, the window heat gain. Notice down at the bottom, this is the estimated solar radiation through various orientations of glass per meter squared, the number of watts per meter squared. Look at, say, the the east and west windows, 285 watts per meter square of window. You can all appreciate a meter square of window on the east or west face. When it's shining, that's 285 watts. That's not a hair dryer, but it's a nice piece of energy that's coming through. And you go, well, I love that in the winter, hate it in the summer. Exactly. And it's incredibly intermittent. Notice there's no geography on this. That is, the estimated solar radiation is pretty constant across the country. Why? Because we all live in pretty much the same latitude. I mean, yes, there's some variation in Edmonton down to Toronto, but it's not like US where we're much wider range. Where we live in our country, we have pretty much the same solar radiation, which means if we have cooling challenges in Toronto, we're also going to see cooling challenges in Calgary due to windows because it's radiant gain. Notice there the factors, the conductive gain through a window, a meter squared of window, is 16 watts. It's the solar gain. That is when the sun is shining. Notice it's about 6 times higher. We could really care less about the heat flow when the sun isn't shining. That's 16 watts per meter squared. When the sun's shining on a window, that's 100 watts per meter squared. That's even with low solar gain windows, that solar heat gain coefficient. So that's a pretty interesting, hopefully, understanding. You're going to put in big windows, you better dial in the specifics of it, and you better help homeowners understand what that's going to do to the comfort in their building. And it's, again, I'll just highlighting that one of the big changes in your renovations, I'll almost guarantee you're adding windows, right? If you're doing a major renovation, I'll bet in an older house, you're adding windows. And in new houses, people are, they're all exhibitionists now. My understanding is people don't want to be outside. They just want to pretend they're outside, right? This is important to understand. So more windows means more intermittent loads. Keep that in mind. And it is about having a deeper conversation about solar gain, solar heat gain coefficients. The window on the right is letting 65% of the heat in. You go, that's great in winter, right? And that's what we always look for, as we wanted that solar gain. Now we're finding, boy, in big glass, that solar gain on an 8 to 10% window to wall ratio, not a big deal. That 0.65 on 30% window to wall ratio, you're going to have overheating issues. And so you want to get to lower solar gain, cut it by 2/3 in this case, by making good window choices. You're going to make that change. And then the mechanical contractor is going to say, yeah, I put in 1 ton per 500 square feet of a house. Not my house. You're not going to, because I've improved the windows by 2/3. Please take that into account. And just a little example of that on this, a little example of that. If I do the heat loss with high solar gain versus low solar gain, not a big change in the heat loss. It's the heat gain that's the big difference, right? 27 down to 19,000. Well, not quite a ton, 3/4 ton difference in a pretty modest house just by making good window decisions. It's pretty important. So that's kind of gives you the essence of design, remembering there's basically 3 formulas. It's just math. It's a good start. At least start with that information, not guessing. Do the math. Now you can adjust. Once you've done the math, now you can adjust a little bit. Well, I want to oversize a little bit or undersize over here, understanding that. But first and foremost, use the 3 formulas to get the size. Next on the list is, how do I move the air around? Now, it doesn't have to be air. Some of you are doing hydronic, that's fine. But how do I deliver the heat or the cooling to the spaces? It will hopefully be useful for you to know that there's algorithms that predict this heat loss and heat gain, as we mentioned. And then there's algorithms that predict the pressures, air flows, water flows, through ducts and pipes. So again, we're using series of algorithms. There's math to this. It's not an art, it's a science. And you can predict how much air moves down a 200-foot length of pipe with 6 elbows, 3 bends and 2 turns, and so on, ups and downs. You can predict. It's not perfect. It's just a good estimation of where things are happening. What is important to understand is our ductwork leaks at the rate of about 10 to 20%. Sheet metal ductwork, properly installed by good HVAC technicians, still leaks air. And you go, does that make any sense in today's world? And it's connected, the ductwork connected to air handlers that vary their flow based on temperature rise and fall and so on. So there's some variability there. And it is, you're trying to control it by a thermostat in the central part of the house that only has an accuracy of plus or minus 1 degree Celsius. I'm trying to give you confidence that there are algorithms that help you predict, that are pretty simple to run. There's software that does it, but they're predictions. They're not real. They're predictions that you get to use as a design tool to get you started, your HVAC designer started. So encourage them to do a proper duct design. So, and then understand that the results will vary. So as soon as the house is built, you're going to have to think about adjusting and balancing to make sure you're taking into account the local needs, the lifestyle of the homeowner. So it's absolutely important for homeowners to understand that there are adjustments that are needed in order to maintain comfort seasonally, and so on. So keeping that in mind is important. And I just thought I'd show you an example of the how duct designs varies. If you look on the left, you're looking for bedroom 2, which is the bottom right corner. That's the room over the garage facing west, compared to bedroom 3 that faces east and is over part of a heated part of the building. How might that change? And if we did the heat loss, heat gain, the conductive gains, we would be able to determine how much air I need using that second formula that I talked about, the airflow formula. That room needs 48 CFM in the wintertime. It needs 66 CFM in the summertime. There's the first lesson. I'm going to have to change the amount of air summer to winter, or I'm going to have to change the window configurations, the shading of the windows in order to keep those numbers. From that, I can determine how big a duct I need to serve that. But you can imagine I got to put in a duct big enough to handle 66. When it's down to 48, oops, now that duct is oversized. So by definition, all ductwork in all houses is oversized, right? Because you have to decide for the bigger of the two in each room of the house. So inevitably, ducts are oversized. What's nice though, is you've done a high performance house, some of these changes, I would say some of the variability leaves this. This is important. For example, what happens if you double the insulation, which we have, right? Over the last 25 years, we've doubled the insulation. We've cut the solar gain in half because we're using low argon windows. And we've cut air leakage by as much as 70%, which means we need about half the amount of air. So instead of that house needing 48 and 66, now it only needs 24 and 33. Notice there's not as big a difference percentage-wise, it's the same, but in terms of actual airflow, not a big difference between 24 and 33. And the ductwork got smaller. I might have needed a 6-inch duct to carry 66 CFM, but I only need a 4 or 5-inch duct to carry 33 CFM. That presents some really nice opportunities for us as we think about designing our houses. But it also presents some challenges, what I want to approach. Notice on bedroom 3, that duct underneath the window. In the past, that used to have 66 CFM coming out of it, and that air would blow over top of that window. Well, now, if I don't change the size of the register, I only have 33 CFM coming out that register, and it might not give me good airflow. So first and foremost, because the airflow volumes have reduced, start thinking about doing a better job of duct sealing. Historically, ducts leaked at 25 to 35. Now, because of code changes, ducts leak at more like 10 to 20 because you seal ductwork in houses. In most builders do. So you want to seal the ducts. We often think, well, that's saving me energy. Not big energy. Most of the ductwork's inside conditioned space, so the heat and cooling staying in the house. What does happen if you don't have accurate delivery of flow, homeowners will adjust thermostats, and so you get some modest energy savings out of doing duct leakage. It's more about comfort. It's more about making sure the 33 CFM you need actually gets to the room and doesn't come out along the way. And the code changed in 2014, requiring at least some duct sealing, but we need to seal even more. It makes the system easier to balance. And I'm going to advocate for a new sealing approach. This is called AeroSeal. Some of you have seen it. It's been around since 1994. A dude comes out, hooks up this sealant mechanism to your duct system, blows it in, and if you look down on the right-hand side along that curve, 22 minutes later, you've reduced duct leakage by 91, 92%. Wow, in 20 minutes of runtime, you've reduced the leakage from whatever it was, but you've reduced the leakage by 92%. That is a huge game changer in terms of being able to direct the flows where you want them to get to. So put that on your list and help your mechanical contractor understand, I'm going to do better duct sealing. So that's pretty powerful. There's a little example. Guess what? This was my house. I had taped and sealed and caulked and so on. But notice what's happening. A 20% increase in flow just to the master bedroom. Wow, how nice was that? And more importantly, when I turn a supply register now in one room, it actually makes a difference in a different room. Notice at the bottom, overall, when I measure the vents, 21% more air actually made it to where you want it to get to, not into the basement, not into the floor joist cavities, but actually to the rooms where I want the heating and cooling to be. So duct sealing is really powerful. And then again, remind yourself that individual room loads have changed. In this case, I've gone to bedroom 3. This room needed 90 CFM for heating, 49 CFM for cooling. But when I get to net zero, now it only needs 45 CFM. And what that means is the velocity, that's the feet per minute, coming out of that 4x10 register, went from 550 feet per minute. Think of that. Travels 550 feet in 1 minute. That's across the parking lot. But now we're down to 270. What does that do to airflow in the house? There's that heating grill at 550 feet per minute. There's that heating grill at 350. Notice what's happening around the room. You just made the building way more efficient, but you didn't get better comfort because the air now comes out and doesn't distribute around the house. It gets even worse in cooling mode. It was pretty tenuous anyway at 550, and now at 350, the cooling doesn't do well. So if you're going to when you do high performance houses and you do better job of loads, your mechanical contractor has to understand if they reduce the loads, reduce the duct sizing, what's happening to the velocity, what's happening to my distribution of air. What we'd really like to get to is maintain that velocity at 550. And here we're showing a high wall, and this is interesting, an opportunity. Rather than putting the ducts out in the perimeter on the floor where they always get blocked by furniture, what if we did high wall distribution? What if we did high wall heating distribution? We actually get a better airflow pattern, and we get to put in smaller duct systems. I'll just show it to you in a second. We could start thinking about smaller diameter duct systems. I'm not talking high velocity systems. What I'm talking about is a better choice of diffusers and duct system sizing to get better throw. It's an actual technical term. The throw across the diffuser, from the diffuser, how far do you want it to travel? So a little higher velocity, slightly higher pressure without impacting noise. You don't want to impact noise, but looking for better delivery. There's a duct system, there's high velocity on the right. It's maintaining, it's just a smaller vent that does a nozzle, if you will, that throws that air across. You don't necessarily have to go to high velocity. And just looking at the amount of air that it moves smaller amounts of air, but at a higher velocity so that I get better throw across the room. So it is an opportunity for you and I and for your mechanical contractor to say, not if, but as I do this better performance of houses, could I change the duct system? Would that present some opportunities? There's a product called RIA that was developed out of research in Pittsburgh by Department of Energy 20 years ago. Imagine that. 20 years ago, the Department of Energy in the United States said, you know what, 15 to 20 years from now, houses are going to heat and cool much differently because we are going to be doing more efficient buildings. How are we going to distribute that air? They gave that contract about $1 million to a group called Ibicus, wonderful firm, who did a whole whack of research on how am I going to distribute small amounts of air in large houses and maintain comfort. And they designed this RIA duct system that can be used on anybody's furnace, a Lennox, a Carrier, whatever. But it includes, look at this smaller grill. That's no longer 4x10. That's more like 2x8 or 2.5x8. And imagining where that could go. Notice them there on the left on high wall. On the right, those are ceiling diffusers that throw the air across the ceiling. And this gives you an opportunity, one, in terms of ducts, what I'm going to do with those ducts, and two, a little bit of sense of better distribution of air, better comfort, more vents in a room so that you get better distribution of air and higher velocities without compromising noise. So designing the system correctly so I don't have noise. The ductwork is actually a variable back one, very specific ductwork. Has somebody said, well, that's flex duct. Yeah, it's not your everyday flex duct. It has I'll call it an external coil. If you look down the center of the duct, you don't see a whole bunch of flutes in it. It's a very smooth duct, a very cleanable duct, very interesting. And frankly, it doesn't have the high mass that a furnace duct has, a sheet metal duct. So it means you get less absorption of that heat radiating off. So the air actually gets to the outer outlet at a much better temperature, much closer to the discharge temperature. So we've advocated here for so using the algorithms to size both the amount of heat and cooling we need, using algorithms to size the ductwork, the distribution system, and then taking advantage of that to find new creative ways to distribute heat and cooling to spaces. So that's should be pretty powerful. And then I'll move on and say that's on the design side. But in the next piece I want to talk about is to say, in today's world, we did a series of algorithms and math to design the system. Now let's use physics and science to actually measure. So we're going from math class to physics class and actually measuring some stuff. And I would say it's one of the big failings that I see. We got so good, so comfortable with our duct designs over the last 40 or 50 years that we kind of forgot that we really should measure this stuff. And it turns out, I'm going to say to builders in this room, you should be advocating that as they put that system in, before the homeowner moves in, that somebody should actually test and see if it's working. Why? Well, because their expectations have changed. Partly because houses are more expensive than they used to be. 2, you've changed the equipment you've put in. 3, those algorithms that we talked about are just predictions. They're not necessarily real. They're just predictions. We want to test. We want to test duct pressures, temperatures, airflow at the air handler, airflow at diffusers, and most importantly, refrigerant checks, specifically on heat pumps. And heat pumps are different. They need more effort, more work. A blue flame in a furnace, 95,000 or 90,000 BTUs, not a lot of variation in how it works. That is new high efficiency gas furnaces. If they say it's 90,000 BTUs, you're getting 90,000 BTUs. The blue flame, yes, you can turn the flame up and down, but not a lot of variation. Refrigerant loops, line set lengths, airflow characteristics, heat pumps and air conditioners have way more variation to their operation, and therefore you need to check. So I want to highlight that. Here's a simple measurement with a digital pressure gauge, the same gauge typically that's used with a blower door, and you're measuring the pressure. This is think of it as the blood pressure cuff. When you go to the doctor for a hangnail, they give you a blood pressure test. They want to know how your system's working. This tells you the health of your duct system. It immediately tells you, is that the right filter or the wrong filter? Is there a blockage in the return? Are the supply ducts big enough? Are they routed well enough? One simple measurement, what pressure is in your duct system. I'm shocked. I do a lot of warranty, forensic work. Homeowners have been complaining for 2.5, 3 years. I go into the house, I do these measurements, and the homeowner goes, "What's that?" I said, "Well, I'm measuring the pressure." I said, "Nobody's done this?" No, nobody's ever measured. All they do is come, put a Kleenex over the register and tell me everything's working just fine. Or they tell me my filter's the wrong filter. And every time I come, they give me another filter and then they tell me that's the wrong filter. Nobody's measuring. This is one of the simplest measurements. Yes, you have to have a digital pressure, a pressure gauge, but every mechanical contractor has one. If they don't, they're not a pro. Say, I need you to measure the duct pressure and see if it's anywhere close to what the design was in houses. As an example, the pressure in the duct system coming off the top, that's the pressure, think about putting your finger over a hose. How do I get the water to the back corner of the garden? I add a little bit of pressure, back pressure. That's what this is about. And if the room over the garage isn't getting enough heat, it may be because there's not enough pressure in the duct at the top of that supply vent. So I can predict immediately. If somebody says problem with the room over the garage, measure the pressure. If it's not close to what it was supposed to be, I need to manage that pressure if I'm ever going to get the flow that I need out the back end. So really important to understand that pressure in systems. And this is where you get to say to a homeowner, that's the right filter or the wrong filter. Just measure the pressure across it. Don't say to them, and I hear this all the time, oh, you shouldn't buy that filter, you should buy this filter. Yes, but I want that filter. It's got a better performance. Oh, it's too restrictive. You don't know if it's too restrictive until you put it into put a test across it. And so 2 simple measurements tells you whether the filter is impacting flow or not. Second is to measure airflow at the furnace. And this is a grid that you slide into the filter slot. It's called a true flow. We just sold a whole bunch of these to energy advisors across the country. Frankly, they quadrupled the number of true flows in the country, and they're all in energy advisors' hands. They're not in the HVAC contractors' hands. They should be in HVAC contractors' hands, but measure the pressures and the temperatures at the furnace. That's important to measure those elements. Encourage your mechanical contractor to do these measurements. And looking for, here's an interesting one, is measuring the temperature off the top of the air conditioner. I get this complaint all summer. It's already started this year. Here we are in May, and it's already started. Yeah, I'm not getting proper cooling. My moisture levels are too high. One simple measurement. What's the temperature coming off the top of the coil? If it's not 10 to 12 degrees Celsius, you're not getting proper cooling. We were at a series of houses just over the last 2 weeks. The units are supposed to be 2 tons. They're actually delivering just over 1 ton. They're thinking about changing the system to 2.5 ton. No, just adjust the system so that you get a real 2 tons. And the measurement we took to get started on this, we're doing other measurements. What's the temperature coming off the top of the duct? If it's not below the dew point, you're not getting dehumidification and you're not getting proper cooling. So simple measurements can be really helpful to you and your customers. And then you should be measuring flow, professionally measuring flow at supply grills, both the temperature and the flow. This is called a flow grid, and it's sorry, not a flow grid, it'll come to me as a hood. Sorry, a flow hood. My apologies. That's measuring actual volume of air. And we would encourage your mechanical contractors, HVAC contractors to have accurate equipment to measure the flow rather than saying holding the Kleenex, actually measuring the flow is vitally important. Next, I said, and last is that refrigerant charge. There's so much variability in how line sets, lengths are, how the systems are working, speeds. You really need to do and verify performance before people move in, that they do in fact have a proper refrigerant charge at the proper temperatures, or sorry, at the proper airflows. And you can't measure one without the other. That is, a refrigerant charge is only as good as your airflow measurement. So measure the flow, measure the refrigerant charge, put them into a test program, and it'll tell you whether the system's working correctly. I can't overstate enough because of the expectations of homeowners. They're not, you need to measure. And if you don't measure every house, the first complaint, take these 4 measurements: the pressures, the flows, the temperatures, and the refrigerant charge. 4 things that you should be measuring in houses. Everybody okay with that? Now, I want to spend just literally 2 minutes on heat pumps. Why are we all so excited about heat pumps? Because they're 300 to 400% efficient. It's just hard to deny. In a world where we want to reduce energy, reduce carbon, if we could find an appliance that's 3 times more efficient, as good as natural gas is, I'm a huge fan of natural gas. We've done a great job over the last 30 years of making them go from 60% efficient to 98% efficient. And that's wonderful. But one more change to get to heat pumps, and now we're 300% efficient. And that doesn't mean we're necessarily getting rid of natural gas. That means when we can use a heat pump, we should be. They're just so darn efficient. And to some extent, you need one anyway. That is, an air conditioner's a heat pump. So you're putting in the box, all you want to do is, instead of saying just straight cooling, now I can do both cooling and heating off the same appliance. So that's why I need to get a heat pump. The nice part is there's all kinds of great options, from the far right ground source heat pumps to mini splits, and down at the bottom right, new air to water heat pumps. On the left, hybrid heating systems, so I can do dual fuel. For those people who are still nervous about heat pumps, sizing, and so on, do a dual fuel, a gas furnace with a heat pump on top. Really, really compelling to say we need to get the heat pumps. And if you want to do dual fuel, fair enough. You put in the traditional gas furnace, instead of putting an air conditioner on top, you put an evaporator coil that looks like an AC, but it's actually a heat pump. The only downside, not downside to this technology, but the downside is the two can't run at the same time. When the gas furnace is on, the heat pump has to be off. That's not a big deal, but it does mean you need to switch over temperature. When am I going to run the gas? When am I going to run the heat pump? From an environmental standpoint, you would say, oh, I want to run the heat pump because it's more efficient. But there will be times we'd say, it's cold out. I don't have enough heat, especially in retrofits. It's hard to make a house efficient enough to do it all with the heat pump. So a gas furnace. Here's another way to use hybrid fuel. What if I bought a heat pump air handler and put a heating coil on top of the heat pump? Oh, now the two could run together, and use, say, a gas water heater, like a condensing gas water heater, to heat a hot water coil that's on top of the heat pump. This is a really nice way to optimize the use of natural gas and the use of electricity, especially in renovations where You try to make the house as efficient as possible, but maybe you can't get it small enough, the heat loss small enough. So this is a nice way to do that. And so there's an example of a combo. There's a tankless condensing boiler or water heater hooked up to an air handler doing the supplementary heat. So one gas line, one vent. This is incredibly flexible in terms of how it uses natural gas, and gives you better comfort in houses. So just I wanted to mention heat pumps as we go through this. Now, just a few slides on ventilation. Thinking about HVAC, when should the ventilation system be running? What did we say? Pretty much whenever you're breathing, right? You need ventilation. It's got to be part of the equation. It's not acceptable. And I still get it. HVAC contractors who say, well, can't run the ventilation in the summer, the AC is not keeping up. Okay, you just told me that you did not size your system correctly. It's not acceptable to compromise somebody's indoor air quality because you can't provide enough heating or cooling, or it's expensive, whatever. You need to install ventilation. And ventilation has three elements to it. It has kitchen exhaust, point source control. It has bathroom exhaust, point source control, and it has continuous capacity. Now, could one system do all three? One system can do two, that is the HRV or ERV, could in fact do your bathroom exhaust. But from an air quality perspective, we're still going to do kitchen exhaust. The single worst or biggest indoor air quality event in your house is cooking. And as much as the bacon smells great, the stuff coming off is not healthy for you. So all those aerosols, all those oils are not healthy. We really need to vent those range hoods. So that's ventilation. And it's pretty simple. I know everybody on this call is probably good for this. What's an HRV and ERV? It's two fans in a box with a heat recovery core. That the only reason I'm showing this slide is to remind you that this should be running continuously. And if it's not quiet, if it's not efficient, if it's not properly installed, then it's not running all the time. And that's not fair to homeowners because the V is important to their health. So imagining that ventilation system, pretty simple animation. The only reason I'm showing it is because this is one of the animations that construction instruction does, could be useful to you. Just imagining how this is working. Stale, stinky air from the house, leaving the house. But rather than wasting that energy and throwing it outside, we're using it to warm up the incoming air. And they're not 100% efficient. They're 70 to 80% efficient. The key that we need to remind ourselves is they need to be designed to run continuously, and your loads for heating and cooling have to be sized appropriately that this can in fact operate. By all means, filter the air more efficiently and so on, but it's understanding. I see this all the time. HVAC contractors and builders. Well, just tell people to turn the ventilation system off in the summer. They don't really need it. No, you need this. And even in old historic houses, Sean, right? Even in old historic houses. And it's not because the building's tight or loose. It's because we've stopped ventilating our houses. In those old historic houses, back in 1910, they ventilated. How? By opening windows. Here we are in 2025. People don't want to open their windows anymore. Why? Because of noise, dust, security. The reason we need ventilation in houses is not because we've made them tight. It's because people have stopped opening windows. Help your homeowners understand that it's not about house tightness. It's about, do you want to open your windows? And the days you don't want to open them, you need a mechanical ventilation system. So just keep that in mind. And there's, again, I'm going to say a pretty straightforward way to size this. How much air do you need? After all, this is an air quality device. How much air do you need? Second, do you want HRV or ERV? And the answer is almost 99% of the time now across Canada, you want an ERV. Why? Because most people are air conditioning. In Graminan, Aaron, are they air conditioning? Graminan, and I'm going to say probably more and more. Why? Because they have so many windows. They want that view. The more windows, the higher the heat gain, the more they want air conditioning. Yep, go ahead and answer if you want, Aaron. I won't cut you off.
Definitely. We want that beautiful south view. So the cooling loads exceed the heating loads. The problem is it's February when we need the air conditioning,
There you go.
and nobody wants to open the window in February.
Right. So we need ERV because ERVs do a better job of managing moisture, tie it to the air conditioning loads. And then you have lots of choices with respect to configurations, model numbers, and so on. This slide is just to say it's not that difficult to properly size and find the right ERV. It's the right CFM, it's the right core technology, and then what's convenient for you in terms of installation. So keep that in mind. I want to mention filtration. It's not the first thing we should do for air quality. We should make tight houses. We should put in proper ventilation. We should manage moisture. But filtration is so darn easy. My fear here is that everybody wants higher levels of filtration, the MERV value, right? There's this guy named MERV apparently who rates filters. No, it's minimum efficiency reporting value. The higher the number, the better. And of course, homeowners want it. And then we have this angst. But the better the filter, the more it restricts airflow. So this is why I mentioned testing systems to help people understand that we can test and decide whether the filter is right or not. What you can do as builders is make sure you put in larger filters, bigger filters, and thicker filters that have more surface area and therefore have less restriction. That's the answer. Everybody wants to standardize on a 16 by 25 filter. There's your math on 16 by 25 down at the bottom. A 16 by 25 filter has a face area of 400 square inches. If you're going to put in a MERV 13 filter, you need a very low velocity, like 300 feet per minute. That means you can only handle 840 CFM through that 16 by 25 filter. If people want to use a better filter at higher airflows than say 2 tons, then I need a bigger filter. I need a 20 by 25 or a 25 by 25. I'm going to ask you as builders, stop allowing 1-inch filters, always at least a 4-inch filter slot, and say to your contractor, hey, I want the biggest one I can get. If you put in a 2025, that means my homeowner can avail themselves of the highest possible efficiency. Please let me do that for my clients. So specify that. Just wanted to show you in terms of those MERV ratings, how well they do. Look at MERV 10 down at the bottom, go across to the particle size that we're most interested in, 0.3 to 3 microns. And you'll notice it really doesn't take out any of the 0.3, takes out about 50% of the 1 to 3 microns. PM 2.5 is what gets deep into the lungs, and that's what we're worried about. Particle matters smaller than 2.5 microns, and this MERV 10 filter only gets 50% of it. That's a bit of a challenge. Your clients want better than that. That's why they want that MERV 11, that MERV 12. Now we're up to 80%. So I want to provide a duct system, design my HVAC such that it's okay for a client to put in a MERV 12. Bigger, thicker filters, please, so that your clients can avail themselves of better filtration technology. I know I only have a few minutes left. I want to do one important topic, and then I'll probably cut it off. Moisture and humidity. Moisture and humidity. It's about maintaining a good moisture balance. 50% plus or minus 5 in summer, 35% plus or minus 5 in winter. How do we do that? This is the right range. 40 to 60, 35 to 55. From a human health perspective, we want to be 35 to 55. It's not get out of the house now because it's 61. No, it's just the optimal range. Don't obsess over that number, but that's where you'd like to be at. And it turns out it's surprisingly difficult to measure humidity. So buy yourself a good meter and calibrate it regularly so that you're using real numbers. It's really difficult. All of these gauges are in exactly the same environment, which is 42%. Notice the huge variation in numbers from 21% up to 51 in terms of the gauges. So buy yourself a good gauge. Turns out there's 4 ways to control moisture in humid weather. You'll be gratified to know the first most important thing you can do is create tighter houses because it keeps the moisture balance more in check. You can control it. Second most important thing you can do, use an ERV for proper ventilation. Third, properly size the air conditioning system. But more and more, you're going to be advocating for a whole house dehumidifier. Why? The AC systems aren't running long enough in most houses to provide dehumidification. On Grand Manan, you don't have enough cooling days. That sunshine on the south face isn't causing problems at night. You need dehumidification in many climate zones. So we need to think about dehumidification because we're doing better windows, better walls, better ceilings, which means our ACs aren't running nearly as much. and we have more latent loads. We're spending more time indoors. We're doing more things indoors that create moisture. You're going to want to start considering whole house dehumidification in your houses, please. Last techie piece is the makeup air. I said to you, we want a better kitchen exhaust. We need to be careful that if we're going to put in tight houses, large exhaust appliances, we could be backdrafting. In most cases, we're not worried about backdrafting because we've gotten rid of combustion appliances. But more importantly, we need to think about negative pressures in houses being annoying. And so as we get to tighter houses, we're going to need makeup air. Just put it in all your bids. If you're over a couple hundred CFM, put in a hole, a controlled hole that only opens. It's called makeup air. We've been doing it for 40 years. It works really well. And dump that air somewhere in the house. It doesn't have to be in the kitchen. Dump that air somewhere in the house. To conclude, one, the changes in your mechanical systems, you have to change your mechanical systems because your houses and your homeowners' expectations have changes. Two, there's lots of new system technologies that are helpful, both in the application, design, and installation, those new heat loss, heat gain tools, for example. Three, test and commission. Remember, 4 tests: pressures, temperatures, flows at both the furnace and the refrigerant charges. 4 tests. 5, move towards heat pump technology. Stop putting in air conditioners, put in heat pumps. Next, understand that heating cooling loads are intermittent and variable, so design accordingly. And more importantly, understand that ventilation filtration are actually continuous loads. And so we have to optimize those loads because they're running continuously. And there's lots of strategic partners, really good partners in this world. The Daikin's of the world are doing some great stuff. Lots of the manufacturers, the ventilation, Broan, for example, Panasonic, are all doing excellent work. So rely on those partnerships to help move the mechanical contractors along a little bit. I'm sorry to rush, and I know I'm right at 8. I don't know if we're allowed time for questions. You guys let me know.
We are absolutely allowed time for questions. Typically, if somebody in the audience has a question, we allow them to jump on and ask. And I suspect some of us have questions as well.
I'm here for the duration. I don't have a beer, but I'm here for the duration, however long you want me to stay.
Well, I'll kick it off. I have a question. So you've done quite a bit of building investigation, and when you go to check whether a system is performing as designed, I assume you ask for the HVAC design.
Yes.
How often is there actually an HVAC design? And I guess the second part of this question is, how often do you have to look at the house, figure out what type of system could have been designed, and then figure out the gap?
That's a really good question. What I would say to you, Aaron, is you may have to get on a boat and move over to the mainland where we have real things going on. I'm kidding, but for example, province of Ontario, it's effectively a code requirement that a heat loss, heat gain, and duct design must be done on every new house. That's not true across the country. But in my market, there's almost always been a heat loss, heat gain, duct design done. That said, we know what furnaces, the common furnaces, the major brand names, in fact, all of the furnaces are designed for very typical pressures. There's not a lot of variation. They all, for example, show data that's, say, 0.4 inches of water column pressures to 0.8 inches of water column. So if I'm measuring a pressure that's outside of that range on anybody's furnace, I go, this can't be right. I don't care what it was designed to. If it was designed at all, I know it's not within the manufacturer's specs. So I'm checking that. And then for sure, I don't think, well, we're doing a back calculate right now, a homeowner under a warranty program that was totally unhappy. We are back calculating and re-proposing a new mechanical system because frankly, they screwed it up. There was a mismatch between the energy rater, the architect, the designer, and the builder and the mechanical contractor, and all would be, not at blame's the wrong piece, not all engaged and not thinking about each other and making decisions on the fly. So the designer said, well, I assume the windows were this. The architect said, well, I didn't know there was a difference between this and this. And the mechanical person said, well, I don't look at windows. That's not my job. And so as an example, the cooling loads were way higher than imagined. And now I got to rethink that system. So generally speaking, we can measure, even if we don't have a duct design, we can make some pretty good assumptions based on typical installation practices of furnaces. And then sometimes we are going back and back calculating and say that room actually needs 50 CFM of heat or cooling. And it can be done. It can be done.
Thank you, Gord. All right. Do we have anybody in the audience who has a question?
I think I talked too fast. My apologies.
I've got a question,
Go ahead.
Igor. Um, so I've heard this, and I don't know if there's, I assume there's some validity to it, but for like a mini split heat pump and a refrigeration setup where it's the refrigerant's put in the field, there's typically like a 2% refrigerant loss per year. Um, at what point would you say that we would require a refrigerant top up?
Never. The TSA standard, sorry to be, I don't mean to sound contrary, but the rules would say contractors are not allowed in today's world, they're not allowed to top up a system. You have to
Really?
top it up. No, if you're a refrigeration mechanic, you'd have to log that, register that, and show that you found the leak. And if you didn't find a leak and weren't confident that you found a leak, then you have to replace the system. That's what the rules say. Now, what's actually happening is another story, perhaps, but the rules would say we're not allowed. And it's an important point because these variable refrigerant VRFs, mini splits, you hear this technology all the time, the variable compressors, the inverter technology, they run at higher pressures in those line sets. So your fittings have to be better. They're more prone to leaks, if you will, because they're running typically, not always, but at higher pressures. And therefore, whatever you used to use for couplings or fittings, you may want to go back and say, no, I need a more reliable system. And there are systems out there. So there's yet another change. If you're going to use inverter technology, you need to do a better job of doing those refrigerant lines. And no, you're not allowed to top them up.
It's interesting because I had a heat pump installed in our house pre retrofit, and I also had a smart Nest thermostat. And I noticed when I first installed it that if I set the heat pump to 22 degrees, the Nest thermostat would read 22 degrees. And over time, there was like it got up to as big as a 2 degree. Like I would have to set the heat pump to 24 to get the Nest thermostat to read 22.
Mm. So and may not be this, but here's another issue. The products that are coming over, the inverter technologies coming over from other places have a different control mechanism. The smarts is not in the thermostat. The smarts is in the outdoor unit. And it's actually making decisions because it's inverter technology. It wants to carefully control the refrigerant, the mix of vapor versus liquid in the lines and in the system. And it's making decisions based on outside temperatures and line sets. So here's the example. We're North Americans. I want my system to be at 18. I deserve it. I spent a lot of money on this house. I want to run at 18 degrees Celsius. Okay. You turn down the Ecobee of the Nest to 18, but the outdoor unit's going, you know what? It's only 20 degrees outside. I'm not giving you full compressor. I'm only giving you 50% compressor. I don't care how low you set that. This is all I'm giving you. And so this is an issue. It's controlled differently. And so they would say, well, no, the thermostat you put on it, it is, you think the smarts is in the thermostat. Smarts is in the outdoor unit.
No,
And
no. Sorry, I should have clarified. My Nest thermostat was used to control my furnace. My
fair
Nest
enough.
thermostat wasn't. It was just reading the temp in the room.
Oh,
So
my apologies. My apologies.
yeah. So I'm just saying that like when I set the heat pump when I first got it, the thermostat was just reading the temp in the room to exactly what the heat pump was set to.
Oh, I see. Okay.
But
Different.
over time, like over I think 4 or 5 years,
Yeah.
that whatever I set the heat pump to, it was different from what the Nest thermostat was actually reading for an internal house temp.
Fair enough. That may be, so I'll still stand by my comment that that's going to be an
There's no
issue.
top up. Yeah.
But second, I will say yes, that presents a problem. I complain to Honeywell all the time. Why did you take away that nice big thick red line on the dial and give us an actual number? This is a problem. People
Yeah.
see the number and they want the number to be the same. And thermostats typically are plus or minus 1 degree. So you could have a thermostat that's drifted. Could be that, could be something real going on, or it could be just that the thermostats have drifted from their accuracy. So
Cool.
this is a
Thanks.
problem for us in houses. Thank you for that question.
I'll jump in with one if I'm curious about air to water heat pump systems and uh, how you maybe see that if that's starting to become a little bit more common here along with cooling as well and like hydronic cooling.
And thank you for that. Yes, air to water heat pumps are coming over now. And there's a couple of Canadian manufacturers, one out in BC, one in the East Coast, and make great equipment. There's more coming over all the time. They have been relatively expensive, but that'll come down. They're slightly less expensive than typical ground source, but they're still considerably more expensive than air to air heat pumps. But air to water coming. So now I can make hot water and I can make chilled water. Okay. Hot water is pretty simple. I know what I can do with that. I can heat houses with it. I can heat floors with it. I can heat hot water and towel warmers. The issue is, as we get colder outside, that heat pump, as you know, has to work harder. And the water temperature is different. Say, for example, you had old cast iron rads that and you go, I want an air to water heat pump because then I can convert it, right? What was running through the hot water rads might have been 160 to 180 degree water. An air to water heat pump ain't going to get you to 160-degree Fahrenheit water. It might get you to 110, 120. Okay, now my radiator doesn't radiate as much heat. Still could be possible. We just have to be mindful that the temperature is going to be different. The other issue is, okay, I go to summer and you do chilled water. How chill is it going to get? 40, 45 degrees? Great. If I put 45-degree water through a cast iron rad, you're not going to, but if you did, what just happened? You have a big piece of cold sheet metal in your house, in this case, cast iron, you're going to get condensation. So what do I do about radiant cooling? Well, I could put that cold water through an air handler. That's okay because the air handler can handle the moisture. But if I want to do radiant cooling, I got to manage the moisture in houses. It's easier to do in Calgary because it's dry, really difficult to do in Southern Ontario, but it's possible. You absolutely could do radiant cooling off that air to water heat pump. What's really nice, and I need to give it the plug, what's really nice about air to water heat pumps and to a large extent ground source heat pumps, all the refrigeration is in that box. You don't need a line set. You don't need refrigeration mechanics. You're now working with plumbers. I believe that's going to be a huge driver, is the fact that we don't have enough refrigeration mechanics and we're worried about refrigerant leaks. And wouldn't it be nice if that was done in a factory and we didn't have to do it out in the field? So that's going to be a huge driver for those appliances. I'm going to say every 6 months you should be checking who's new in the market, what are the prices, where's the training. They're coming quick, and they're going to be a viable technology.
Yeah, thanks for that. I keep seeing more and more information about it. We haven't had an opportunity to use a system like that, but it's sort of on my wish list when the right project comes along to sort of see how that might fit.
Yep.
Yeah, Gord, great presentation. I think all of us need to improve and constantly just refresh our information about mechanical and delivering comfort. I can say honestly that until probably 5 years ago, I didn't fully understand the need for makeup air, except in extreme situations where we were really good at selling big fancy kitchens. We put in 5-foot ranges, 6-foot ranges, and then have a 600, 900, 1200 CFM fan. And now that we're seeing even in an airtight building, like a 200, 300 CFM fan can depressurize the whole building,
Yeah.
and the need for dehumidification. So I'm curious from your side, the more builders I talk to understand the need for makeup air. It's not really pushed by at least code examiners in the municipalities that they live in. Is there a rule of thumb? because they'll tell you, I don't have an issue in my buildings. Is there a rule of thumb that we can learn about when it comes to either sizing that range hood to say, okay, you're in the territory of needing one, or is it coming down to looking at what the pressure drops are?
No, you make a good point. There's not just a rule of thumb, there's an actual standard. It's called F300, depressurization standard. And it tells you exactly how to do this. And the good news is if you're doing blower testing of
Yep.
your house, you know in advance, I'm going to be at 1.5 air changes. That you know what that means. One, it took 50 pascals of pressure to
Yep.
create 1.5 air changes. How much, sorry, at 50 pascals, what pressure, how much airflow did it take? Okay, it took 300 CFM to depressurize my house to 50 pascals. What if I put in a 300 CFM range hood? Every time I run it, the house is going to go to minus 50. And you go,
Mhm.
does anybody care? Well, you tell me. Are people going to be annoyed when every time they open the door, there's a whistle? Are people going to be annoyed when they turn on the range hood and it doesn't move 300 CFM? It only moves 150? I'll give you the example. I built a house, point 0.2 air changes, point 0.2 air changes. I turn on the range hood, which is only supposed to move 250, and it goes, can't find any air. And it only moves 60 CFM. Guess what? I'm not getting the removal of pollutants off that range hood. My dryer goes, ooh, and the clothes don't dry. And so I and so now the new standard says if your fan is going to create more than a 25 pascal negative pressure, have a problem. And you can predict that knowing the size of the house and before you build the house. Okay, here's the volume of the house. I'm going to be at 1.5. That's my goal. That's where I end up. I know right now that I need makeup of X amount because 25, and it's a fairly simple, it's a very simple formula. Your blower door tester, if you're not, well, you do this stuff. You know how
Yep.
to do this. It's pretty straightforward. There's log functions in it, but my iPhone does it for me. I can put the number in, it'll tell me what's the flow at 25 pascals. That's the number I have to hit for makeup. So you have it exactly right. It's not a rule of thumb anymore, but there's an actual measure.
That's brilliant. I think too, RetroTech has a digital gauge that we can
Yes.
just plug in the data and see the numbers. And I recognize like we used to be more renovations, a lot of kitchens, main floors. Something we had never done is ever managed, unless we're doing an addition or a whole house gut, is measure the current air tightness while we're making changes to the mechanicals. Because often we'd be taking out a smaller, OTR over the range with really low exhaust rates, putting in some monster thing, right? With a industrial hood and industrial range and, chef kitchen. But I think this is something we need to add to our workflow for interior renovations too.
From a safety perspective, I do need that. So 25 pascals is the upper limit if you
Yep.
don't have chimneys. If you have chimneys, natural draft appliances, it's 5 pascals. That's a health safety issue. 25 is an annoyance slash range hood doesn't work. If you have a chimney, chimneys can overcome roughly 5 pascals negative pressure. So here's the classic, right? We're doing a big renovation, the
Yep.
old house. We still want the wood burning appliance look. We don't want to lose the hearth. We're going to put a gas log set in it because we don't want to actually put wood in the house. We just want to look like a fireplace. And now I put in the big kitchen. Oops, that's a disaster waiting to happen. So we 5 pascals for chimneys. So again, you can define that
Yeah.
well before you build the house, and you can say to your clients, "Hey, if you want to keep that fireplace open hearth, I really need to make sure I put it in this big hole in your house or put in a makeup air system." We're doing one right now, large new house, and they're going to put in a makeup air system because they don't want to compromise. They want 2 wood burning appliances, and they're going to be good. They're not actually going to be, goofy ones. They're going to be airtight, good, guillotine doors and so on, but they want that
Yep.
open hearth but they still want the 2000 CFM range hood. All right, we're doing makeup here. And in that case, it's got a heater to it. And so in most cases, you don't need to heat it, but in this place, they'll heat it.
And I'm assuming you'd also group in like if they still have an older natural draft hot water tank.
Well, one, get rid of those for sure.
Right.
They are natural draft water tanks. To be honest, it's time they go away. They are very lazy venters. There's not enough heat coming off of them
Mm-hmm.
to vent. And again, I don't mean to alarm anybody, and the gas company is going to say they're safe. I get that. Yes, they are technically safe, but they are very lazy venters. The technology's moved on. We should too. And you should take every opportunity to say, hey, I'm doing this reno. I know it has nothing to do with the reno, but I'm going to help you get rid of that natural draft water heater.
Good call.
In your place with the point two air changes and your range hood and dryer fighting for oxygen, what did you end up? What was the solution?
So the solution is you saw that little makeup air damper. I have a duct from outside that runs into there's a little knee wall area, which playroom for the grandchildren and so on. So I dump it into there with a nice louver and grill, dampers in place. I have a pressure switch in the range hood line and a pressure switch in the dryer line. And each one of those senses movement of air. Call it a flow switch. You could do it electrically when the dryer's on, but that's harder to do, frankly, because you have to break into the electrical line. So these little pressure tabs, and you're going to say, well, the pressure tabs will get dirty. Every now and again, you might have to pull them if you're hearing the dryer go, again, you might pull the sensor. It's easy to pull out. You will find time goes on. Broan, for example, is starting to put dry contacts in their large range hoods for makeup air. So they're starting to recognize Broan was 12 years ago. Broan said, should we be worried? I mean, talk about a responsible company. We're the largest manufacturer of range hoods. Should we be worried? Yeah. All right. So they started providing makeup air options on their website. They have a calculator online. I think it's more complicated than it needs to be. It's more for Americans, I'd say. We already know this stuff. Like we're doing blower tests, so we know this stuff. So we don't need their calculator. But they sell equipment, and now some of their larger range hoods, let's say more expensive range hoods, have a dry set of contacts that would allow you to open your makeup air.
And did the duct or the damper that you put in make the difference? And like what size
Oh,
was it?
absolutely. Absolutely. And in my case, it's, both are modest airflows, dryer. The makeup airs, come in 6, 8, and 10 inch. So I put in the smallest one, 6 inch. I probably only needed a 5. You're going to say, how do I size it? That too comes with a formula. So it's not a problem. So 6 inch. And again, damper opens. I don't need to heat it. It's not on that long. And it's into an area. You don't want to dump it over Papa's easy chair. But you put it into the mechanical room or put it into a place that, it's not occupied all the time. And for me, it's not been a problem. These clients that I was speaking of with the large house, they imagine entertaining whole families in the weekends. The range hood's going to be running a lot. They don't have to worry about whether the air is going to be cold, and it's a lot of air. So they'll put and you can buy makeup air kits that have heaters in them and so on.
Awesome.
I will say, I'll give you the confidence. We used to have to cobble together the bits and pieces, but I put in makeup air in my own house 30 years ago. I mean, this is not new technology. It's just new awareness, to Connor's point. We just hadn't really thought about it.
Yeah.
But now there's a standard F300.
Excellent.
Super helpful. Gives me one more chance to use a blower door, even for a kitchen room.
There you go.
Perfect.
Good.
Well, if we don't have any more questions, we'll give the last call for questions. Either way, if somebody comes up with a question, we'll stop. But I really want to thank you, Gord, for coming on this evening with us and helping spread awareness about a topic that is just really not talked about enough. We know about it, and we talk about it when things go wrong, but we don't talk about it ahead of time enough, I don't think.
And thank you for the opportunity. I'll say I love the fact that Beer and Banner's doing this. I think I said, Jeremiah, I've been to one or two in person, just if I happen to be there, but I'm often on the road. So if I can help, you folks will know that. Just call me. We'll put it on the schedule. I'd love to help if I can. I just love you folks spreading the word, building that awareness. So thank you.
Thank you.
Beautiful. Thanks, Gord.
Thanks, Ken.
Thank you, Gordon. My next trip to Ontario, I will try and swing by.
Yeah, come by. We're pretty proud of the new office here in Guelph. And we actually have some wall sections and stuff which you can immediately tear apart like every builder likes to do and say, oh, I wouldn't do it that way. I do it this way. And that we love that. That's what it's about. So we'd love to host you. That'd be great.
That'd be awesome. We'll talk flashings and HVAC.
Yes, exactly. Cool.
Incredible.
Thank
All
you.
right.
Thanks, good.
Well, thank you everyone for joining us. And that brings to close another amazing episode of BS&BEER Canada. And we will see you all on the next third Thursday.
Thanks, gang.
Thanks.